Well, we're starting now with science as dialogue. So science as, once again, a discussion, okay? But, most of us would say, or many of us in America would say, well, what's there to dialogue about? Something either is or it isn't. And it's the job of science to find out the difference. It's about the rational understanding of the world. Is that true? Well, not completely. There's an element of that, but there's other things going on. That's a very simplistic view of, of what science is, okay? And so, but that classical view of science still prevails in the public mind to a great extent. And that being that science is objective, science provides the data we need for innovation and solutions, and most importantly, the science is value free. If you've taken a sociology class before, you know that the goal is to be value free, particularly in social science. But that we're human, we're all human, whether we're scientists, social scientists, whatever we are, teachers, parents, we all have values. But it's particularly important when you're doing something like science, once again, whether it's the natural sciences or social sciences, to try to be value free. And the more you are aware of your own values and what you may be bringing to it, and how that may affect your research and that type of thing, the better a scientist you are. But as you'll see here, environmental sociologists point out that the firm boundaries that we just stated, it is what it is, it's data, it's value free, are neither possible nor advisable, really, for scientists to operate that way. So we know that politics can shape our behavior, for an example, and that's really not necessarily a bad thing. It's politics that brings us the regulations and the rules that make our food safe to eat and our medicine safe to take, and a variety of other things of that nature. So those are political actions and movements, legislation that makes that possible. And so also that small d democratically funded, tax-funded research situations and entities. So yeah, politics. You don't necessarily want all politics out of science. So because politics in and of itself aren't evil, it really depends on what the politics seek to achieve. So whether that's something for a few, like the subsidies to the oil companies. I know I keep bringing that up, but it's such an obvious one, or the tax breaks for major corporations, or whether it's politics that is involved with justice for all. So once again, no simple answer, no right or wrong. It depends, right? So let's take nuclear fission as an example of the political aspects and the pure science aspects of this science as dialogue discussion. So uncontrolled research on nuclear fission, you get the atomic bomb. Controlled, you get nuclear power. Okay. Well, we got both, right, with the way the research was done. And the motivations, political, for the research. So if you look at Marie and Pierre Curie, I'm sure you know that they were the Nobel Prize scientists for discovering how to split the atom and do fusion and that type, fission, nuclear fission, that type of thing. Their work it constitutes pure scientific discovery, okay? But it also was a political process because they needed money to do their research, and where they got a lot of that money from was uranium mine. People who owned entities, corporations that owned uranium mines. Okay, to see this connection now. um, they wouldn't have had the resources to do their research without that money. So it was neither pure science, what they did within the lab, or pure politics either. It was neither a pure material cause, trying out how to split the atom, nor a pure ideological cause. It was both. It was a combination of both. So, even scientists often believe that what they're doing is pure science and removed from the funding source and that type of thing. And the example of that, they give you the quote from Edward Teller, who ran the Manhattan Project, which invented the atomic bomb to be used in Second World War, and most famously on Hiroshima and also Nagasaki, the second one, but the first one that was dropped was on Hiroshima. So it was the scientist, and here's what he said, Edward Teller, kind of in defense of himself, because many of the scientists working on the atomic bomb were horribly, horribly, horribly torn about what they were doing. So Edward Teller's quote, "It was the scientist's job to discover the laws of nature, not to pronounce whether the laws permitting nuclear fusion ought to be established for the construction of a hydrogen bomb." Okay. So they were like theoretically separating themselves completely from the political aspects of what their research was going to be used for. So it's an example of what's called, that statement, the naturalistic fallacy, a claim that is, which means a claim that because something is a certain way, it ought to be that way. That what is real is good and what is good is real. But if you connect the what is and the ought, what ought to be, what is, if you connected that, what is and what ought to be, the real and the good, that would make science a moral project, wouldn't it? Okay. You would have to decide, well, we could do this, but should we? And I always think of cloning and Dolly the sheep when I think about this or talk about it. Yeah, you can clone critters, and I suppose ultimately people, but should you? Should you do that? So those are the kinds of the what is and what ought to be decisions that scientists. Another example is, we moved in modern medicine from declaring death when either the heartbeat or respiration stopped. Now it's brain death. People can still have a heartbeat and still be breathing. Why did we do that? Because it made it easier to transplant, to get organs for transplantation. And there are still other cultures that just say, no, they're not dead yet, So there's another example. Can we do that? Yeah. Should we do it? It depends on a lot of things, doesn't it? Where you come down on transplants, whether you think that's appropriate, whether you think that's okay, a whole bunch of things. So it doesn't take much thought to see, I hope, that avoiding the connection between, the real and the good, the ought, the what is and the ought, is an example of actually making the connection, because to have those two ideas, that there's what's real and what's good, is if you avoid making that connection, then you're also having a concept, a way of thinking about this stuff. So here's the thing. If we do science without ethical debate, what we get is no science that will ever be explored that would be an alternative to nuclear weapons. We would get no regulation for rural wells. Okay, we would just keep opening Pandora's boxes without having any other. Remember, in the previous lecture we talked about you don't explore alternatives if you believe this is just the way it is. Okay, so in other words, our sense of what ought to be, unavoidably shapes what we look for and create. And if we don't look for alternatives, we won't find any. Therefore, science is unavoidably shaped by the ought, whether it wants to be or not, whether it wants to acknowledge that or not. But that's not necessarily good, cause for alarm, because it gives you options and it's scope for dialogue. So what could be done differently is an example of dialogue with things like feedlots, for example. What could we do differently? There are other, what could we do instead of using gasoline cars? It opens up dialogue. Now, this black box concept is really an interesting one. What it's saying is that science, through its aura of objectivity, and its often very inaccessible language to most people, can seem like a kind of black box. And that's a term coined by social scientists. What that means is it seems like in this black box, the end results of science can seem like they're logically determined from the beginning, instead of what it actually is, which is a debate with constantly evolving ideas that are and it also seems, this box seems impenetrable, that the boundaries are very, very, very firm in this black box of science. But sometimes those boundaries collapse and then all the pieces fall out of that black box. And when that happens, a very interesting thing occurs. And it's a paradigm crisis. A paradigm is the way we think about things. And a paradigm crisis results, which sometimes can lead to a scientific revolution. What about the Earth not being flat? Forever, people thought that the Earth was flat until we found out that it wasn't. There's still a flat Earth society, I'm aware of that, but you get the point. That led to a scientific revolution. What about poor Galileo, that the Pope, made him stay locked up in his villa and never write anymore or talk anymore to anybody, when Galileo proved that the Earth revolved around the sun rather than the sun revolving around the Earth, because according to the church at that time, the Earth was this kind of the central thing that God ever created, and everything revolved around that, actually, scientifically and metaphorically. Well, Galileo said, no, look here, look through the telescope. You see, that's not true. And man, they shut him up immediately, banned his books. Sound familiar? That type of thing. So that's when the black box collapses. Wow, we have to all adjust, right? Our ideas and our concepts about things. So at such times, to put it mildly, assumptions are challenged. And those two examples, I think, are good ones, the flat Earth and the Galileo example. So having your assumptions challenged, it can be scary. And I want to warn you against assumptions, just in general. I see so many things happen to people and things that don't have to happen, and issues arise because of assumptions people are making that have no basis in reality. Okay, let's look at the actor network. Okay. And what this theory does is it traces relationships, or this idea, I should say, not theory. Well, it is a theory, but it's an application here. It traces the relationships between human science and technology, and it finds the social ecological ties which have been disappeared, right? Which have been black boxed out of the picture. Those social ecological ties. Things like consequence, right? So I think I've said this before, but did you ever want to ask people or situations, what did you think would happen? Because that's what consequences are. If you don't think a process or an action through, you very well may not like the consequences that occur. Okay. So you have to think ahead, right? What could be the outcomes? What are the possible outcomes of these actions I take or behaviors or ways I think, right? So these things um, that the actor network theory does is it kind of blows open that black box idea of this all being some mystery, and it brings it out into the light, particularly things like consequence. So the actors, whether or not they're human or thinking or intentional, um, they are, so it could be other species, for example, they have consequences for each other, right? That's something that isn't talked about in the black box, but by having mutual consequence for each other, these actors are linked in together into networks that shape what other actors can do. So it enables both possibility of people of network, the possibility of networks, and it also can lead to constraints of behaving in certain ways because of the consequences. Okay, if you think about it that far ahead. Um, it's really important to understand that actors doesn't just mean humans, and they suggest that they call us actants, but I don't think we need to do that. Just remember, actors can be a variety of things, other not just humans. Okay, so how do you apply this actor network theory, which is a dialogic perspective, to Fukushima? I think this is a very interesting process to work through. So the Fukushima plant, nuclear plant, constitutes the humans running it, just as the humans running it constitute the plant. It's a network. Neither thing works without the other, right? The reactors did produce energy, and in that sense that they produced the energy, they had their own agency. Okay? An agency is defined as the ability of any being, object, or network of beings and objects to act in the world, to take action in the world. So the reactors did produce energy. They did make that act, okay? But the key point about agency is it's not the same as intentionality, right? You can have agency to do something that you don't really intend to do. Your action made it happen, but you didn't intend for that consequence, right? So, in this example of Fukushima, a pipe or a reactor may act in the sense of producing energy or leaking or whatever, but it doesn't intend to do any of those things. It just does them because of the mechanical situation. Okay. A being, however, intends and can seek new means and ways of achieving those new means. So some actors in an actor network, in the actor network theory, are intentional, right? And some are not. It's mostly the humans, of course, that are intentional. But even with non-intentional stuff, there can be surprises. There again, pipes break, earthquakes happen. Okay. So consequently, actor networks are never completely orderly or predictable. They're what this social scientist who thought of this theory, the actor network theory, called mangles. You might call them messes or tangled up stuff, but he calls them mangles in this sense. So the humans intended, because they have intention as well as agency, they intended to build a nuclear power plant to make money and provide energy. Okay? The power plant didn't intend to melt down, but it did. What resulted was a mangle of money, policy, scientific boundaries, and black boxing that produced the awful outcome. And by black boxing and boundaries, once again, they mean just keeping it, not thinking about the consequences when they did this so much as what they wanted to, the purpose of the Fukushima plant. So let's look now at disasters fast and slow. So determination, that idea of determinism, can't protect us from all the material worries and uncertainties of life. Sometimes, as we know, the worries can actually become realities, even disastrous ones. We just talked about that with Fukushima. Now, disasters don't affect only individuals, but they also threaten those mutual ties that link us all together. Sometimes they bring people together. We see that a lot. We talk about that a lot, don't we? In disasters, people helping each other and finding meaning and, all of that stuff. But other times they can leave social ecological ties completely shredded and leaving community members destitute and alienated. Those kinds of reactions mostly come after disasters where humans, tend to have caused the disaster because all your faith is gone. It's one thing, if a volcano explodes. It's another thing when nuclear power plants go wrong because of human issues. So if you take the common phrase, quote, natural disaster, floods, storms, wildfires, and we use the terms act of God or nature strikes again, right? I have to say, and it's a way of, the reason your book is using those terms, it's a way we talk about and think about things that we think of as being natural disasters, okay? I want to say that this is changing a little bit now in our dialogue because people are talking about the human behaviors that have caused some of the increases in those things. Because, floods, storms, wildfires used to just be thought, they actually pretty much were just acts of God before human beings started, or nature strikes again type of issues, before humans started fiddling around with the stuff that causes them now. So as long as we continue to use that terminology, as long as the causes of disasters are attributed to natural or supernatural causes, it remains in the morally innocent realm of natural conscience. Nature says so, it's just nature's way. And that's simply not true. It's a facade. And, deeper than that, it's a lie. However, as we know, much of the flooding, wildfires, hurricanes, droughts, etc., are caused by human activities when you peel that onion again and find out what the causes of them actually are. And they use the example of I don't know if you remember when this happened in 2019, there was film about it all over, the poor koalas and people and everything, all the other animals, but, a lot of it focused on the poor koalas. Those huge bushfires in Australia in 2019, there was the divide in Australia and everywhere else in the world among people who saw them as natural disasters or a natural disaster and a tragedy. Yes, granted, a tragedy, but a natural disaster. And those who viewed them as a turning point of climate change, okay, which most scientists did actually view them as a turning point of climate change. Well, now think about it, framed as a natural disaster and a tragedy. That wouldn't be preventable, would it? A natural disaster. Yes, granted, it's a tragedy, it's a horrible thing, but it's a natural disaster. You couldn't have prevented it. A turning point, framing it that way, thinking of it that way, would be preventable. Because a turning point means something happened to get it to that point, right? Where it got that bad. So, such realizations can make us angry. Okay. And I think about Greta Thunberg, Thunberg, right? She's angry, and rightly so, righteously so. And it can undermine our trust in the security of the world and each other. And so trauma, it's a kind of trauma that's especially difficult to recover from. And I would say today, look at the increase in violence and shootings, and it's just insane what's going on, because that social mutual thing has broken down to such a great extent with all the amazingly difficult issues we're facing, from COVID to wildfires to wars to on and on and on. So there's a profound difference between disasters that can be understood as the work of nature and those that need to be understood as the work of humans, which is called in social environmental sociology, this great term, a new species of trouble. Okay. And those new species of trouble, like the bushfires we just talked about, or the Fukushima disaster, have several characteristics in common. And this is Kai Erikson who developed this idea of a new species of trouble. Here are the characteristics: the crumbling of trust and the shredding of community ties is one. The next one is a chronic social trauma that victims only slowly recover from, if at all. Chronic means ongoing, right? In physically, it means something that's ongoing. This is psychological trauma, that ongoing, that victims only slowly recover from. And the third one is a pervasive sense of dread about what the future will bring. All very sad, right? And Erikson predicted that the experience of many about about COVID-19, which is the crumbling of trust because of the feeling that the government and employers aren't adequately protecting us. And that is so true, especially for, essential workers. It's just, I have a daughter who's an essential worker, and they were not protected enough at all, and no one wanted to confront the customers. In the management said, oh, don't confront them about things when they're whatever. And it's very disturbing because it does erode trust of not being properly protected by the people that are supposed to do that for you. That's one. This next one is the chronic social trauma of isolation from family and friends that happened with COVID, and for children too, especially from school. And then the third one is the pervasive dread that eventually you or a loved one may get the virus, and with the possible severe consequences. So they're applying this concept of a new species of trouble to the COVID epidemic here. So according to Erikson, the new troubles contaminate our minds as well as our bodies. And some of those previous things we just talked about are examples. Whereas natural disasters suggest a lack of control over processes that are beyond humans, the new species of troubles implies a lack of control over processes that we thought to be within the reach of humans, that we thought humans should be able to take care of and control. So those violations of trust are deeply disturbing to humans, and that element of dread exists, and especially with things like toxic exposure, like the Flint water crisis and that type of thing, Grassy Narrows. It's what Erikson calls slow violence. Okay. They go on, and they keep occurring, and nobody does anything about them. So, what are normal accidents? There's a general belief that although we can't prevent natural disasters, we can at least anticipate and prepare for them, and there's a high degree of psychological comfort in this. There is definitely. Technological disasters, in contrast, are viewed in the opposite way. We often understand them as preventable, and that's Greta Thunberg again, but there's no way to fully anticipate and prepare for many of them. So one of the things we should do is view technologies as systems from two different dimensions in order to understand their potential for failure. This is really interesting to try and get this here. So the first dimension, to help us understand the potential for failure of these systems, is the extent to which a system's interconnections are linear or complex. So in a linear system, the components are spread out, they're real easy to see, they're easy to segregate or separate, and they're easily substitutable. So if something breaks, you can substitute, something else along the way. And they have very little feedback between each other, those components, those parts. So the example of that is a very basic assembly line. A complex system is just the opposite, or reverse of that. The components are very close together, they're hard to pull apart or substitute, and they have a lot of feedback. The example of that is a nuclear power plant. And then the second dimension of understanding this is the extent to which a system is loosely coupled or tightly coupled. What coupling means is the degree of slack or buffer there is given between two items. Okay. There wasn't much slack or buffer at Fukushima, was there, when that pipe broke? Okay. So the example they're giving you here is that Line 61 tar sands pipeline. It's both complex and tightly coupled. If one component fails, it can create stress on all the other pipelines connected to it. And it did, didn't it? But another example is a university. That's a complex system, but it's loosely coupled. If one or an occasional or even some of the students fail, others won't just because one did, right? Okay, and then a basic assembly line is linear. Yes, it's true. We just talked about that. But it's also very tightly coupled, because if one worker makes an error, it will have consequences down the line. And you can get a humorous take on that by watching Modern Times, the clip from Modern Times, the Charlie Chaplin clip. So what can we learn from this? A very profound observation. If in systems that are complex and tightly coupled, therefore, we should expect occasional serious accidents. If not exactly specifically predictable, they certainly are unsurprising. Now, if you know that that type of system, which is complex and tightly coupled, if you know that that type of system is much more likely to have serious accidents than the simple uncoupled ones, then that's predictable, that's possible to happen. And so one should be not only just be unsurprising, but one should take greater care, because a further important point is that complex, tightly coupled systems are invariably risky systems. Okay. So, there's always this surprise, is the point of the book, that, oh my God, that happened, but it was often predictable. So all of the disasters in this chapter, and especially Fukushima, lead to another observation. I love the way they put this. We could use a good dose of humility with regard to our rationalist confidence in technology. I would certainly agree with that. In fact, I'm going to repeat it. We could use a good dose of humility with regard to our rationalist confidence about technology. The second point being, no amount of rational calculation of risk probabilities could have predicted any of the disasters in this chapter or the previous chapters that we've studied. Okay. So what we need is a more qualitative than quantitative approach that understands accidents as a normal aspect of systems. So you would always build in the fact that there is possibly, and in some cases likely to be, accidents, and have it down what you're going to do about it in various situations. Expect the unexpected, right? And employ a precautionary approach to systems with a high potential for catastrophic possibilities. And another important point is that technological systems are social systems. We're just winding it up by going back to that concept again. It's not human error on the part of the operators that leads to technological disasters, but it's the forms of social organization, which is what technology really is, that creates situations where there are, yes, highly trained, capable people who are nonetheless unable to quickly and correctly enough to prevent, to quickly and correctly act quickly enough to prevent a disaster. Okay? All those people who work in those plants are highly trained, highly capable people. Okay? Now let's look at science and technology as political. We're almost through. So coping with disasters is easier, of course, if you have more political power. And power differences have implications for the science that gets done and the science that doesn't. So what science gets done and what science doesn't get done has a lot to do with power differences. So as an example, the Wisconsin Department of Natural Resources didn't require an environmental impact study of the risks of an oil spill from Line 61 because of lobbying from the oil company. Who had more power there? The oil company, of course. Here's an even better one. I'm sure you'll all appreciate this. Did you know that all the original breast cancer research was done on white men for years? Years and years and years. Now, yes, men do get breast cancer, but it's a tiny percentage of breast cancer cases, as I'm sure you know, compared to that of women. And also here's more, until the mid-1980s, that recently middle-aged white heterosexual men were the unquestioned normative standard in most medical research. And then those results, of course, were generalized to the whole population, including women and people of color. So another example of that that's more recent is heart disease. For years, the symptoms of heart disease were the symptoms that men had. So when women would go to the doctor, and if they didn't have the same, heart disease symptoms that men did, they would never even, check. And then the woman would have a heart attack, but very different symptoms. So now at least there's some education around that. Even lab mice today are proportionately male. I think that was so funny. So challenges to this kind of normative standard of white male heterosexual men being the standard for all of us were actually made through social movements and political action, so that can change things. So what has happened over the years is there's been pushback on that. So it's called the biopolitics of science. And that's changed drastically for the better. As breast cancer is another example, which is now more focused on research and preventative treatments, and also in empowering women around breast cancer instead of the victimization model that was around for so long. So politics can shift things, as we've looked at all through this chapter, through social movements for change. And people tend to forget that social movements and change are political actions. Okay. So science is, when science is aware of its political implications, that's a really good thing. If it's consciously aware and has a good conscience, it can strengthen communities and contribute to forms of knowledge. But of course, there are other forces at work in science. And, this is where it's very depressing what's happening, because research used to, for most of it, the majority of it took place in publicly funded institutions. Now it's just the opposite. Research takes place in private corporations outside of democratically controlled institutions, small d again, right? Democracy. Okay. And then often the funding sources aren't divulged for the research. So in the US, 71% of research is done in by industry, and only 14% in colleges. And then there's some other percentages of things in the text that do them. But it used to be the reverse of that, colleges and universities and industry with research. So to conclude, finally, you're probably thinking, the point of politics is to figure out how best we can all live together with each other and the rest of the world. That's the ideal, of course, point of politics, and not how it manifests itself many times. But that is the point of a political system in general. But we still do need a much better politics of science than we currently have. One that's more open, one that's more transparent, not so much in need of private and industry funding. And because private and industry funding invariably have their own agendas, right? All right, that's it for this week.